Okay guys, next we will discuss the electric potential energy. As we know that the potential energy can be defined as the energy stored in a body due to change in its position. It's called potential energy. So electric potential energy means if we bring a charge from one point to another point, then the energy stored in their charged particle is called electric potential energy. Let's suppose we have a charge. I call it Q1, which is at point O. And let's suppose we are bringing another charge from point Q2. The charge is Q2 from point A to point B to this point. Now I suppose that the distance from this charge Q1 to this point B is RB, and also the distance from this charge Q1 to point A is RA. And I also assume that both these charges are positive charge. Now, in order to bring this charge Q2 from point A to point B, we are doing work. And the work done in moving charge from point A to point B is equal to integral of F dot dr, where the limits of the integral are from point A to B. Now, where F is the applied force, F is applied force. We suppose that the charge Q2 is moved from point A to point B with constant acceleration. So if it is moving with constant acceleration, what it means? It means that this charge is in dynamic equilibrium. By dynamic equilibrium, my means is the sum of all the forces acting on this charge will be equal to 0. So we can say that the applied force, so here this is the applied force due to which we are bringing this charge from A to B. But there is another force which is called electrostatic force, because both these charges are positive charges, so they repel each other. So the force exerted by this charge Q1 and Q2 is in this direction, which is applied force. So these two forces, applied force and electric force, they are equal in magnitude but opposite in direction. So the direction is opposite, that's why I put a negative sign here. This is the applied electric force exerted by charge Q1 and Q2, and we know that the exerted electric force exerted by charge Q1 and Q2 is Q2 into E1, because we know that the electric field of charge Q1, which is, let's suppose, the source charge, is equal to the force exerted by the source charge, which is charge Q1, over a test charge, which is Q2. So from this we get F1 is equal to Q2 E1. So I replace this applied force by this minus Q2 E1. This is equation number 1 and this is equation number 2. Using equation 2 and 1, we have work done in moving the charge Q2 from point A to point B is equal to minus Q2 times E1 dot dr. This is equation number, let's suppose, 3. Now, the work done in moving a charge from point A to point B must be equal to the change in potential energy associated with electric force. Or we can say that the work done in moving a charge from point A to point B is equal to the change in potential energy. Because we have a change in potential energy. Here we have one kind of potential energy. Here we have the different potential energy. So if we move from here to here, then there is a change in potential energy. So the work done will be equal to the change in potential energy. This is equation number 4. Comparing equation 4, 3 and 4. We have delta U, change in electric potential energy, or change in potential energy, is equal to minus Q2 times E1 dot dr. This is equation number 5. Now Q1 is a point charge and its electric field at a distance somewhere at r is E1, which is 1 over 4 pi epsilon naught q over r1 square, r square, because we consider it to be r. So if I replace the value of E1 by this one, then my change in potential energy will be equal to minus Q2 into integral. The limits are from A to B, yes. A to B. A to B, 1 over 4 pi epsilon naught Q1 over r square into r unit vector dot dr, if this is a vector quantity. Now bringing the constant outside of the integral, we have minus Q1 Q2 over 4 pi epsilon naught into integral from A to B r cap over r square dot dr. Now here we have this r cap dot dr, which is equal to r cap dot dr vector, can be written as its direction times its magnitude. Now r cap dot r cap, we get 1. So this is equal to dr. So this equation will be equal to minus Q1 Q2 over 4 pi epsilon naught we have integral from A to B dr over r square. This is the change in potential energy, delta E. Now I can write it as delta U which is equal to minus Q1 Q2 over 4 pi epsilon naught. If I integrate it, I will get minus 1 over r into, in limits are from A to B. So this will be equal to minus Q1 Q2 over 4 pi epsilon naught into minus 1 over RB minus 1 over RA. Because point A is at a distance of at RA, A is equal to RA and B is equal to RB. But this is plus because upper limit, which is this, minus into lower limit. So there is a minus into minus 1 over RA, so this will become plus, positive. So if we simplify it, we get Q1 Q2 over 4 pi epsilon naught into 1 over RB minus 1 over RA. This is the change in potential energy, delta U. But change is, we are moving from point A to point B. point A to point B. So change will be, here the potential in is UA, here the potential in is UB. So we have the final potential minus initial potential. So delta U will be equal to UB minus UA. This is the change in potential energy of a point charge moving from point A to point B. Now, suppose the charge is separated by infinite distances. Suppose we have this charge Q1, which is at point O, and charge Q2 is somewhere at infinity. I call it RB is equal to infinity. This is point B. And I am bringing this to point A, which is at a distance of RA. So at infinite distance, this charge has a zero potential. So potential at infinite distance, UA, which is at infinity, is equal to 0. And also the distance RA, this distance RA, sorry, this is A and this is B. This is RB and this is RA. Like charge Q1 is at point O and charge Q2 is at point A, but point A is at infinity. Like the distance from this charge Q1 to Q2 is infinite. So RA is in infinity. Now we are bringing this charge Q2 from this infinite distance to point B, which is at a distance of RB. So if I put, so at infinite distance, this charge has a zero potential. UB is equal to 0 here. So UB is equal to 0. UB, which is at infinity, is equal to 0, and also RB is equal to infinity. Putting this value in above equation, so we get UA, sorry. We are moving from A to B. Yes, this is point A and this is point B. Point A is at infinity, so UA is equal to infinity. And the distance from point charge Q1 to Q2 at point A is infinite. So this is RA. So I can write it UA, which is at infinity, is equal to 0, and also RA, which is at infinite distance from the charge Q1. So using this value in above equation, we get UB minus UA0 is equal to Q1 Q2 over 4 pi epsilon naught 1 over RB minus 1 over infinity. So from this we get Q1 Q2 over 4 pi epsilon naught 1 over RB minus 0. UB minus UB is equal to Q1 Q2 over 4 pi epsilon naught 1 over RB. So we can write in general, this is, let's say, equation, this is 6, then this is equation 7. This is at point B. If we are not mentioning the point, but we suppose that we are bringing this charge to a point where the distance is R, then in general we can write the potential of a charge, electric potential energy of a charge at any arbitrary distance is equal to 1 over 4 pi epsilon naught Q1 Q2 over R. I just remove this P factor here and the rest of the equation is same. This is the electric potential energy. So we have how many equations for the electric potential energy? One equation is U, which is 1 over 4 pi epsilon naught Q1 Q2 over R. One is this equation. And the other one is for the change in potential energy, delta U, which is equal to minus Q into integral of A to B E dot dr. This is another relation. We can also write it as minus Q integral from A to B E dot dl. If we consider the length element, we replace just r by this length element. So we have these two relations which we will use again and again in the rest of the calculation. And now next I will consider my potential energy of a system of charges. Potential energy before we discuss the potential energy of two charges, like if we bring one charge in the field of another charge, but here we will discuss a system of charges, energy of a system of charges. Suppose we have charge Q1, okay, which is already present at this point, and we are bringing a charge Q2 somewhere from infinity. This is the direction of charge Q2, okay, from infinity to this point. This is Q2. Then we know that if I suppose the distance to be r1 to here, then from this equation the potential u1 will be equal to potential u1. u1 means bringing charge q2 from infinity to this point is 1 over 4 pi epsilon naught q1 q2 over r12, which we already did here, like bringing a charge. This is charge q1 q2 from infinity to this point q. This is at distance r, is this one. So here the distance is r12. Next I bring another charge. Let's suppose I am bringing another charge from infinity. This is it. Let's suppose infinity to this point. This is charge q3. Then now there are two charges here, so the distance of q1 and q3, the distance between q1 and q3 is r13, and the distance between q2 and q3 is r23. So if I bring this charge q3 from infinity to this point, then we have two potentials now. One is from charge q1 and the other is from charge q2. So I call it u2, which is bringing a charge in the field of q1, which is 1 over 4 pi epsilon naught q1 q3 over r13. And also there is another potential stored due to this q2, which I call it u3, which is equal to 1 over 4 pi epsilon naught q2 q3 over r23. Now this is obvious, because if there is one charge, then there is a potential which is u1, which is equal to 1 over 4 pi epsilon naught q1 q2 over the distance, which is r12. Now if I bring another charge q3 from infinity to this point, which is q3, now there are two charges here now. One is q1 and one is q2. So the potential energy will be of two kinds. One is due to q1 and one is due to the interaction of q1 and q3, and the other one is due to interaction of q2 and q3. So one is, I call it u2, which is due to interaction of charge q1 and q3, and the other one is, I call it u3, which is due to interaction of charge q2 and q3. Now potential is a scalar quantity, so we can add it simply. So the total potential u total will be equal to u1 plus u2 plus u3. If I put the value in all this, we have this 1 over 4 pi epsilon is common. so I'll keep outside. So we have Q1 Q2 over R12 plus Q1 Q3 over R13 plus Q1 Q2 Q2 Q3 over R23. This is the potential due to 3-point charges. If we have more charges, then we can apply this relation to that one also, which I will discuss later. So this is all about electric potential energy. In next video I will discuss about electric potential. So we have to differentiate the two quantities. One is electric potential energy, and the other one is electric potential. These two are completely different. So you got the idea of electric potential energy. In the next video I will discuss electric potential. Thank you.